So I'm very happy to reintroduce Luca for lecture number 4. Let me just say the last lecture will be tomorrow at 10:15. In the end, it will be tomorrow at 10:15. So see you here then. And without further ado, Luca.
Great. All right, so let me start with a brief summary of what we've seen last time about the perturbative quantum effects. First, for non-supersymmetric black holes, non-supersymmetric, near extremal. Well, we computed the partition function using the gravitational path integral, found that as the temperature becomes small, quantum corrections become large, and explicitly the one-loop determinants were given by some power of the extremal entropy times e to the s naught, e to the minus beta times m naught. And then there was a very important temperature-dependent one-loop determinant that scaled like 1 over m break times beta, 3/2. And the semi-classical piece for the deviation of the free energy as a function of the temperature. The important thing that we emphasized last time is that this becomes very important when the temperature goes to 0, or when we approach extremality, or equivalently when the inverse temperature is infinity. And we also studied the density of states of this theory. It goes like s naught to this power. That depends explicitly on the matter content of the theory, times e to the s naught times an integral over dE. Break. Let me forget the order 1 factors. Times sinh up to pi square root of m minus m naught. Break. E to the minus beta m. So from here, we see that even though we managed to account for a lot of perturbative corrections in 1 over g Newton, we still found that in the non-supersymmetric case, we got a continuous spectrum. Because rho of E has support on the entire positive real line. And this means that puzzle 4 that we posed in the first day, in the first lecture, about the discreteness of energy levels remains unresolved, even when accounting for perturbative corrections in 1 over g Newton. I should contrast this with the supersymmetric case, where in that case, resolve. In that case, we found that there's a discrete set of states that were the BPS states that could be independently seen from the gravitational path. And as I've said, a really good probe for the discreteness of the spectrum is a quantity called the spectral form factor. So let me reintroduce that. That's an object that we will work a lot with in the next 2 lectures. The spectral form factor is the product of 2 partition functions that are analytically continuous and complex conjugates to each other. The point is that when looking at what the gravitational path integral gives us, we find that the spectral form factor decays forever, in contrast to what we expect from a conventional quantum system. And that's just somewhat of a restatement of the fact that the spectrum is continuous. So let's see how it actually looks like, how the spectral form factor actually looks like. Well, just multiplying 2 of these guys together, and analytically continuing beta, we get the following, that the spectral form factor is e to the 2s naught minus 2 times beta m naught, 1 over absolute value of the breaking scale times beta plus it cubed, and e to the 2 pi squared m break inverse 1 over beta plus it plus 1 over beta minus it. So if we're interested in the behavior of this function, when the time, Lorentzian time, becomes very large, this is when we expect the spectral form factor to start growing again. We see that this expression roughly goes like e to the 2s naught divided by m break cubed times t cubed. And this should be contrasted with the pure semi-classical answer, which didn't account for this one loop determinant, which goes like a constant at very large t. And there's some e to the minus 2 beta. Okay, so if I look at the spectral form factor on the log-log plot, I see that it decays forever. So why do we care about the spectral form factor? Well, as we shall see, and as I kind of hinted in the first lecture, the spectral form factor is also connected to the two-point function evaluated in a thermal field double state. And it would be a big problem if, from the boundary perspective, that two-point function decayed forever, like the spectral form factor. So we expect that if we resolve the paradox for the two-point function eventually growing and plateauing, we'll also resolve the same issue for the spectral form factor. So we want to see that eventually, somehow, there are corrections to our formulas that lead to a growth and eventually a plateau.
Hey, Luca.
Yeah.
Maybe you mentioned this at the end of the last lecture, but in the supersymmetric case, when we have the delta function in rho of v, what does the spectral form factor look like?
Well, I think at late times it's just dominated by this huge ground state degeneracy. So the leading order spectral form factor doesn't have a problem actually in the supersymmetric case because you do see this discreteness.
Because of the delta function.
Yes, yes. But before I continue to resolve to say what type of corrections can lead to this corrective behavior that I pointed out here, let's talk about something a bit more physical that will also help us understand the relation between the spectral form factor and a correlator. So, namely, physically, an observer cannot actually measure thermodynamic quantities directly, such as a partition function or entropy. They measure some properties of the environment, right? So they measure how the environment reacts to perturbations. Namely, what they can measure to are correlation functions or properties that essentially correlation functions dictate. For instance, the rate of Hawking radiation that an observer measures is also related to the correlation function of the field that's associated to the particles whose Hawking quanta the observer measures. Essentially it can be rewritten in terms of a transform of a two-point function of that field. So essentially, by knowing correlation functions, we can understand how what an observer actually sees in an environment. So today we'll be focusing on the simplest type of correlation functions, namely two-point functions. And we'll be talking about two types of two-point functions, Euclidean two-point functions, in which we have an observer at the boundary of this of our ADS2 patch, inserting two operators with a proper time tau in between. So this is O at, let's say, time 0. This is O at, let's say, time tau. In such a way that on the other side, the distance between these 2 points along the proper distance along these 2 points along the boundary is proportional to beta minus tau. So this is one type of two-point function that we're interested in, and the other type of correlation function that we're interested in is more directly related to what Maldacena used in his version of the information paradox for the two-point function in the thermal field double state. Namely, you consider an eternal black hole that can be considered even in 2 dimensions. And we look at the two-point function between an observable inserted on the left and some observable inserted at the right. Time t. And we can always keep the observable at the right at time 0. If I change the time of the observable on the right, I can always perform a translation for both the left and the right using the dt killing vector that's defined in this geometry in the bulk. To rewrite that correlation, that two-point function, as a two-point function where the right observable is always set to 0. So because this state here, the state that we're preparing is the thermal field double state, which, as I said in the first lecture, it's an analytic continuation of a half disk from Euclidean signature. These two-point functions are actually related for an analytic continuation. And namely, if I consider the two-point function O of tau, O of 0, evaluated at this inverse temperature beta, and fixed tau equal beta over 2 plus IPT, then what I recover is the observable on the right, namely the two-point function of O left, which at time t, in a thermal field double state at inverse temperature beta over 2, or right position 0, PFV beta over 2. So by computing two-point functions, these two-point functions in Euclidean signature, I can also immediately obtain the two-point functions in Lorentzian signature. Now, the issue with these two-point functions is that just like the partition function receives strong quantum corrections from the fact that this boundary is fluctuating, and therefore the actual distance between the 2 points is also fluctuating, this means that the two-point function itself can receive strong corrections either as the temperature becomes small, or as we shall see, as the Lorentzian time becomes large. So, before I continue, let me rewrite this two-point function in Lorentzian signature in a useful manner. So we saw in the first lecture that the thermal field double left at time t derived at time 0, E of V is equal to a sum if my energy levels are discrete. It's equal to a sum over all possible pairs of energy levels, O E prime squared e to the minus beta over 2 e plus e prime e to the minus beta e plus e prime plus IT e minus e prime. Now, in our model of gravity, we didn't find discrete energy levels. We found a continuum, but we can replace the sum by an integral over a continuum of states. So taking the density of states found from the gravitational path integral, we expect this two-point function to look like integral d prime, rho of e prime, where this rho is the formula of sinh of 2 pi square root of e that I wrote earlier. O e prime, absolute value squared, e to the minus beta e plus e prime. Sorry, I think there is a factor of 2 here, so it's beta over 2 and beta over 2, e to the IT e minus e prime. So essentially, in order to find the two-point function, the only thing I need to do is find out what this operator is when expressed in the energy basis, in the basis of energy eigenstates. So this is E O E prime, absolute value squared.
Okay.
Yeah.
Here you can do something even more primitive, which is study one-point functions, right? Because they are 0.
Yeah. They're 0.
But in one higher dimension, 3 dimension, these are non-zero, right? The thermal one-point function. And you have one-point function.
Yes.
So, you can expect this has a ramp plateau structure, maybe in this case.
As a function of what?
As a function of beta plus IT.
Yeah, I haven't thought about it, but yeah, maybe one can consider that in higher dimensions.
Sure.
Look, if you wanted to do the one-sided thermal two-point function, that would just be like the same beta instead of beta over 2, basically.
Yeah. So you mean if we wanted to move one operator here?
Yeah.
Yeah. Essentially, the only difference would be how you do the analytic continuation of the Euclidean two-point function. So instead of tau being beta over 2 plus IT, I think tau would just be IT. Because essentially the difference between these 2 points is just the Lorentzian time evolution.
So you're interested in this case for reasons that will become clear, or?
No, so I'm interested in this case because this is the one in which Hahn phrased this black hole information paradox problem, in which he noticed that essentially this two-point function decays forever in a higher dimensional eternal black hole in ADS. And yeah, that's what I briefly mentioned in the first lecture. Does that answer the question?
Yeah, there was an analogous thing you could formulate for the one-sided.
Yes. There's an analogous one there. I think both of them will get resolved in the same way. So I'm just using this one because it's also a little bit clearer to see this decomposition into energies by directly using the definition of the thermal field level. For rewriting both the correlator that you mentioned and this Euclidean correlator in the energy basis, one has to insert a complete set of states, but it's not like that difficult either.
Sorry, Luca.
Yeah.
The formula which connects the Euclidean time with the thermofield double is some kind of saddle point formula.
No. This applies at any.
It's exact.
It's exact. Yes. Okay. So essentially, to determine what this operator is, what we have to do is determine the overlap in gravity between a bra in which we have some energy E and some geodesic L connecting the two sides. Then insert the propagator in ADS2, the matter-to-matter propagator in ADS2, G of L, between these two sides, and evaluate this in an inner product with a ket that has also a geodesic of length L and an energy of with value E prime. So the question is, what are all these ingredients? This is mostly schematic, but now let's discuss how to essentially determine what would be a wave function in JT gravity that gives you the overlap between an eigenstate E and state that has fixed length between these 2 points, L. So this we can think of as psi E of L, the overlap between E and L. First, let me write a useful formula for what the distance. Well, before I do that, our purpose now is to essentially study the quantization of the Schwarzian theory once again, but this time from the canonical point of view. What I mean by that is instead of studying the path integral over the Schwarzian theory, we'd like to find these sorts of wave functions. So the question is, can we rewrite the Schwarzian theory as a function of distances between boundary points, instead of as a function of this reparameterization mode that we called T of tau? So how do we go from T of tau to this basis in which the distances between points is fixed?
Just in the above diagram, do we sum over all intermediate lengths?
Yes. So, yeah, I'll make that explicit in a second. So the idea is that we have like the idea is to view this as having some wave function that transitions us from having a fixed energy to having a fixed length. But here we can think about this operator. We can think about this operator that we're inserting as actually inserting integral over dl, g of l, ll, where g is the propagator between 2 points in ADS2 that have distance L in between, and we want to evaluate it in the E prime basis. So, yeah, so that's why we're interested in this overlap between E and L. You had a question?
No, should I think of this as just basically a change of basis? We worked in an E basis here, but then we introduced the L basis.
Exactly. Yes. We can think about it as a change of basis that has the nice property that we can immediately read off what correlators are at fixed energies. So a useful formula is that for the distance between 2 points in ADS2, and when written in terms of upper half Poincare coordinates, So when d's s squared is dz squared plus dt squared over g squared, the distance between the geodesic distance between the 2 points is d, which is given by e to the minus d is z1, z2, t1 minus t2 squared. It's an easy exercise given this metric to see that this is the geodesic distance. Good. Now, what we're interested in are distances between boundary points, right? Boundary points have the property that if we look at z, so z1 is z at some time tau1 on the boundary. We saw that if we look close to the boundary, z as a function of the property time tau1 was related to t as a function of the proper boundary time tau1 prime. This came from from imposing that the induced metric on this boundary was constant, if you remember. So there was this plus corrections that went like epsilon squared. Similarly, z2 is z of tau2 equal epsilon p prime p2 plus dot dot dot, which means that the renormalized length between two boundary points is given by t prime times tau1, t prime times tau2, divided by t tau1 minus t tau2 squared. So this is e to the minus L, L of tau2 minus tau1. So where L, you'll notice that the only thing that I did from going through from D to this L is that I absorbed this factors of epsilon. So L as a function of tau2 minus tau1. So L as a function of time, just D as a function of time, minus 2 log epsilon. So D was slightly divergent as I sent the boundary of ADS2 closer and closer to, this boundary of space-time closer and closer to the boundary of ADS2. But I can still talk about renormalized length between two boundary points, exactly like I do in higher dimensional versions of ADS-CFT. And now we can imagine that we set tau1 to 0 and rewrite tau2 as just tau. And now we can actually gauge fix what t of 0 and t prime of 0 is for an SL2R transformation. This just chooses essentially what point on the space-time I call the origin. And it turns out that after you gauge fix t of 0 to 0 and write t prime of 0 as a constant, you get that the Schwarzian action, which was 1 over m break integral d tau Schwarzian t of tau, can be written as an integral of 1 over m break L dot squared over 2. So this is an integral over d tau minus m break e to the minus L. Essentially, you just use the formula for the Schwarzian in terms of derivatives of t, use this formula for e to the minus L, and plug that answer into here. And this is a rewriting up to total derivatives, which means rewriting things in Hamiltonian formalism, we can rewrite this action as I pi L, L prime, minus H, or saying that the Hamiltonian is equal to m break times pi L squared over 2 plus e to the minus L over A. So pi L is the conjugate momentum to L. So rewriting this, the action in this form means that now we have the ability to quantize the theory in yet another way. Instead of doing the path integral, we can literally try to diagonalize this Hamiltonian, right? So let's see what this Hamiltonian, how to diagonalize this Hamiltonian, and what are its eigenfunctions and eigenvalues. So it turns out that if you set pi L b minus I ddl, you get the following Schrodinger equation that you have to solve. So what we're actually solving for now are precisely these eigenfunctions that we were looking for, right? When we solve for eigenfunctions in the energy basis, this is essentially the inner product between E and L. Great. And now you can literally plug this equation in Mathematica and solve it. And it has solutions which take the following form. Psi of L, that again represents the transition between fixing the boundary energy to E and fixing the distance between these two boundary points to be L, or the normalized distance to be L, is 4 up to a normalization constant that so far we haven't determined. It's 4k 8 by square root of e to the minus L over 2. So these are the wave functions, if you want, in of the Schwarzian theory in the energy basis. This, yeah. Yeah, maybe the better way of well, there's multiple ways to arrive at this Hamiltonian. One way is to talk about a two-sided Hamiltonian. That's a sum of h left plus h right. Uh, because what? Yes. Here the distance is like it's still the distance between two points on the same boundary. There it would be the distance between 2 points on different boundaries. But it's like the analytic continuation of this picture, right? We can analytically continue this to obtain the thermal field double state, and then still talk about the distance L in between. I didn't want to go through this Lorentzian derivation because it's a bit more complicated, and I just wanted to get to the main result for the correlators. But yes, there. Uh-huh. I think it's just a rewriting of the Schwarzian action that's convenient for this canonical quantization. Yeah, you're confused. Maybe the confusion is that I'm fixing one of the points and letting time vary this way, which seems like a slightly unusual way of evolving wave functions. Is that the issue? Maybe. Okay. Well, maybe I can say a little bit more afterwards about how to also derive this in the thermophile double state. Well, it's just a trick to obtain the wave functions without necessarily going to Lorentzian signature. Yeah, so it's just a trick. Well, this equation, what I was going to say as well, is that this equation can be viewed as the analog. Well, it can be viewed as the a version of the Wheeler-DeWitt equation. That you can obtain by imposing the Wheeler-DeWitt constraint and the momentum constraint, and evolving your Wheeler-DeWitt wave functions along this direction. So it's essentially the same. It's essentially a quick way of deriving a Wheeler-DeWitt equation. You could also, do it the longer way, in which you write the metric in ADM formalism, and then just follow what Wheeler and DeWitt did. And if you impose that the extrinsic curvature of the slices that you're studying have k equals 0, and you impose that this length is fixed, you'll find precisely the same differential equation. Okay. So a first property of this Bessel functions is that if I look at renormalized lengths that are very negative, this Bessel functions are exponentially decaying, which means that these wave functions have very small support for small length differences between these two boundaries for any finite energy, for any non-zero and finite energy E. And for large lengths, it turns out these Bessel functions are oscillating, so that's the regime in which they have support. Good. The second thing is notice is the orthogonality relation between these Bessel functions gives you an orthogonality relation between wave functions, which is that the integral over dl psi e of L psi e star e prime of L prime tells us that the two energies E and E prime have to be set to be precisely equal. And the normalization factor that appears in front of this delta function is precisely the density of states that appeared, that we derived from inverse Laplace transforming the partition function when doing the gravitational path integral. So this row of disk is precisely contains the factor of sinh of 2 pi square root of E over n break that we derived earlier. So this is nice because we found a set of wave functions that are delta function normalizable, and the coefficient that is supposed to give us the density of states precisely reproduces the density of states that we see at, through the quantization using path integral. And we can also talk about wave functions when instead of fixing the boundary energy, we fix the boundary proper length. And this is just given by taking a Laplace transform of the previous wave function. So we can define psi of beta over 2L. So again, we fix the geodesic of length L on one side and glue it to a fluctuating wiggly boundary whose energy might not be fixed, but whose proper length is fixed. b beta over 2. And this is given by an integral over dE, rho disk, rho, yeah, I'll use this notation, rho disk of E, k of 2I square root of E, e to the minus L over 2, minus beta E over 2, with the property that now, if I integrate two of these wave functions against each other, using the orthogonality of Bessel functions that I wrote here, essentially one factor of rho disk of E will cancel, and I'm just left with an integral over dE, rho disk of E, e to the minus beta E, which is exactly the partition function at inverse temperature beta. This can be viewed as the analog of the Euclidean preparation, the analog of the Euclidean preparation of the thermal field double state. Okay. So now, given that we know these wave functions, we're at a point where we can talk about correlators. The only ingredient that we're missing is the boundary to boundary propagator in ADS2 for a particle of mass delta, given that the distance between these two boundary points is L, we normalize distance is L. A simple calculation shows us that this propagator is just given by e to the minus delta L. So now the only thing that I have to do to determine the correlator, given that the boundary is fluctuating, to determine O of E prime squared, I just have to glue the wave functions and the fixed energy basis to each other. So this was my bra. I insert here. Sorry, let me just draw it here. Fixed L. This is my bra. Sorry. This is my ket. And this is the propagator insertion that inserts this line in between the two. And now I just have to glue these two in order to obtain what this element is, what this operator can be expressed as in the energy basis. And the result that we find, this integral can be done exactly if you plug in the Bessel functions from before. It's a product of gamma functions. So you just find that it's gamma of delta plus I square root of m break inverse times E1 plus square root of m break inverse times E2 times gamma of delta minus plus I square root of m break inverse C1 minus square root of m break inverse times E2. So this absolute value squared, and this is divided by 2 m break inverse to the power 2 delta, gamma of 2 delta. Okay, so this is a bit of an ugly expression, but it tells us everything that we want to know about a two-point function, right? So let's analyze what happens to the two-point function in different regimes.
Can I just ask perhaps,
Yeah.
you evaluate OEE squared, is that equal to the integral or the square of the integral? Because,
That's a great question. So it's equal to the integral because these states, these gravitational states that we're preparing are like the analogs of the thermal field double. So they're entangled from the boundary perspective. There are states that look like EE. This is a state that looks like E prime, E prime. And the operator that you're inserting is like an operator on the left and an operator on the right, even though we're just inserting a single propagator, which means that what we're obtaining on the left-hand side is the squared operator from the boundary perspective. From the bulk, we're just doing a single integral over the intermediate lengths at which these two operators can be placed. That's a great question. Thank you. Any other questions? Okay. Fantastic. And remember that to evaluate the Euclidean two-point function, the only thing I have to do is integrate dE1, rho of E1, dE2, rho of E2, against O of E1, E2 squared, e to the minus tau E1 minus beta minus tau E2. Right, so let's analyze this formula for the Euclidean or Lorentzian two-point function in different regimes. So the first regime is the semi-classical regime. So when do we have a semi-classical regime? Well, it's when no other length scale compares to this to the length scale associated to the breakdown energy, m break. So in other words, when m break inverse is the largest length scale in the problem, meaning that this is much larger than beta and much larger than tau. In that regime, we can evaluate this integral by saddle point, because essentially we can rescale all these energies by m break, and the factor in front of this energy after this rescaling becomes extremely large. So evaluating that by saddle point, what you find in Euclidean signature is that O of t, O of 0, takes precisely the form of a correlation function that's derived from conformal invariance, from imposing conformal invariance or imposing that the bulk has an SL2R isometry. So this is the answer that you find if you do. It's a bit of a lengthy calculation, so unfortunately I don't have time to go through it. But the point is, if you plug this formula in here and use the expansion of gamma functions for large arguments, you can evaluate this by saddle point, and this is what you find. So now, so this was Euclidean. And to evaluate things in the Lorentzian configuration that I mentioned earlier, in which we have an operator on the left and an operator on the right, I told you we just have to set tau to be beta over 2 plus IT. So plugging that in there, essentially this sign becomes a cos squared, and we're left with a function that's exponentially decaying in Lorentzian. So the 2-point function is therefore e to the minus delta 2 pi t over beta. Maybe pi t over beta. Great.
But what is the power of the Euclidean result?
Oh, sorry, this is delta.
Okay, sure.
It's the scaling dimension of the operator in question. Does that make sense?
Yeah.
And this is just the answer that can be derived from conformal invariance. Okay. Let's now analyze a different regime, a different Lorentzian regime. When we look at very late times, very late Lorentzian times, so when t is now bigger than the breakdown scale, and it's much bigger than beta. Well, looking at this formula, at very long Lorentzian times, what you see is that in the exponent, this thing is the same as e to the beta over 2 minus beta over 2, e1 plus e2, plus it or minus it, doesn't matter, plus it, e1 minus e2. So at very long Lorentzian times, what happens is that we're probing smaller and smaller energy differences, right? If we're probing small energy differences, we can rewrite this integral over dE1, dE2 as an integral over the sum over E1 plus E2 and the difference of E1 minus E2, and expand rho E1, rho E2, and this operator at small energy differences. So what we find to leading order is that we just find this, nothing special happens to this operator as the difference between E1 minus E2 becomes small. These gamma functions don't have a pole or anything like that. So this piece vanishes, but we're just left with gamma of delta, which is non-zero. So at leading order, we find that O left, O right in this regime is given by some number that comes from the integral over the sum of E1 minus E2 times an integral over the difference times e to the I difference times t. So this in principle just gives a delta function in time, in Lorentzian time. This is not quite valid because we're evaluating things at very long Lorentzian times, while this only has the port at t equals 0. So we have to look at the next order correction, for which again we can separate out the contribution coming from energy differences, and we get an integral over d theta. We just expand this function as a function of energy differences. D theta times d delta times delta squared times e to the I delta t. So this guy is just a Fourier transform of a polynomial that scales like 1 over t cubed. So what this means is that even though at a semi-classical level the 2-point function was decaying exponentially, when you include quantum corrections, that's for both the density of states and the exact form of this operator in the energy basis, so we look at this 2-point function in between beta. So here the only assumption that I made in deriving this result was that I was looking at Lorentzian times that were much longer than the Euclidean temperature at which I was preparing the thermal field double state. we find that initially, if I plot this on a log-log plot, there's an exponential decay followed by this straight line that gives this 1 over t cubed behavior as a function of time. So even though, so first of all, now the power, the power with which things decay with time is completely independent of delta, which is kind of an interesting feature of these strong quantum effects. And the second thing is that the decay law for this two-point function has completely changed due to these perturbative effects. But nevertheless, the two-point function, even when including all order corrections, just like the spectral form factor, still decays forever. So there's still a problem. And perhaps as a final comment before I move to talk about the resolution to this problem, as a final comment, the same similar analysis tells us that quantum effects become important in another limit, which is that which is when beta and tau are much bigger than m inverse break. So this was the regime that occurred very close to extremality when the temperature went to 0. So let's write the two-point function in Euclidean signature now is an integral over dE1. The density of states is approximated by a square root in the limit in which the energies that dominate are small. And when I make beta and tau to be large, what's happening is that I'm looking towards states that are very close to being extremal. So the density of states is approximated by square root. So I won't keep order 1 factors here, but it's approximated by square root of E1 divided by m breakdown, instead of having an exponential growth in the density of states times dE2, square root of E2 divided by m breakdown. The expression that I wrote for what O is in the energy basis is completely smooth. As I said, E1 and E2 towards 0. So I just have to evaluate this, the matrix element of O in the state 0, 0, when I'm interested at very small temperatures. And then I multiply this by e to the minus beta minus tau, E1, e to the minus tau, E2. So this is just a Laplace transform of square root E1, and this just gives a Laplace transform of square root E2.
What is the range of over which you integrate it?
0 to infinity. So the answer that you find for this above integral is that the two-point function is thus given by O00 divided by beta minus tau to the 3 halves and break inverse and break inverse tau to the 3 halves. So essentially, this is the form, which is a form which is again the temperature, the dependence on Euclidean time between the 2 points is completely independent of delta. So a universal feature that I could probe as if I wanted to test the validity of the CFT, if I had near extremal black hole right here on the table is to just measure a 2-point function for operator of different masses and check whether their 2-point function is completely independent of the separation between the different operators. And perhaps I just want to also tell you just an informative comment that similar rules can also be used to derive any correlation function for a string of any number of operators. So one can derive O of 0, OT1, OTN in the geodesic approximation when including all quantum corrections in 1 over g Newton and including the leading temperature dependence. Okay, perhaps let's take a 10-minute break.
Maybe some questions.
Yeah, questions? Yes.
Do you have an interpretation for the delta of t at large t?
Sorry.
Yeah, this first term then.
Not really. It's just the piece that vanishes very quickly.
Yeah.
It's
the leading one when you do this expansion in small
Yes.
like, energy difference.
Exactly. Yeah, like at large t, this is really the first thing that you see. Like if you actually use the exact formulas and plug them in Mathematica and look at how the plot looks like at long Lorentzian times, you'll see that it goes like 1 over t cubed. I think this delta is probably an artifact of the expansion.
It has no physics to it.
I'm not sure. Yeah, I don't think so.
This T1/3 is also delta independent, capital delta independent.
It's 1 over t cubed.
Yeah.
Yes. There's the only delta dependence comes in this free factor.
No, so I was thinking because here you said that there's no delta independence. There's delta independence, right? So no matter.
The delta. There's also delta dependence. I just meant in the time Euclidean time dependence is delta independent. So this operator, if you look back at your formula, the formula for this matrix element depended on delta, right? The gamma functions that I wrote down also involve the deltas.
Okay, so just the time decays the independence.
Yeah, just the way in which things evolve with time is completely delta independent. Which I think is a really nice probe that is worth exploring more for these near extremal black holes. So for instance, if you have a proposal for how to construct these states using a different effective description, then one way to test that proposal to see if you're correctly reproducing quantum effects in gravity is to show that the 2-point function behaves in this way. Okay. I'll be right. Yeah. Great. So we saw that earlier that even if we include quantum effects, there was a problem for the 2-point function that was similar to the one for the spectral form factor, in which the 2-point function decays forever. And I already hinted that non-perturbative effects can help us address this problem. Now, the problem about talking about non-perturbative effects in real near extremal black holes is that there are many, many perturbative effects that we didn't take into account, as well as stringy effects, so on and so forth, that we don't have any control over. We've written the leading terms in 1 over temperature expansion and a 1 over S0 expansion, but there's many perturbative corrections, for instance, in 1 over S0 that we have no idea how to derive. Because, well, we can't do the path integral, the gravitational path integral fully. So in order to talk about non-perturbative corrections in a sensible way, we have to talk about a toy model. Namely, we'll just simplify the effective field theory that we wrote down to only contain the massless 2-dimensional degrees of freedom. and compute non-perturbative effects, compute the contribution of non-perturbative effects in purely in this two-dimensional theory. So the theory that the toy model that I'm considering is just a theory of pure JP gravity. So no matter degrees of freedom coupled to it, no other KK modes that come from the dimensional reduction, nothing at all aside from a dilaton and the metric. So let me just write the action again for probably the fourth time or however many times I've written it. So there's a topological term in this toy model, and then there's a bulk term which couples the metric to a dilaton field, and that also contains a boundary term. And previously, when we treated this as an EST for higher dimensional black holes, we saw that integrating out the dilaton fixes r minus 2 to be equal to 0 exactly at all points of the geometry. In other words, it inserts a delta function of r minus 2 in the path integral. And this Gibbons-Hawking-York term at the boundary of ABS2 gives us weights that we can use for different boundary fluctuations, boundary-shaped fluctuations. But there's one thing that we didn't discuss in this context of EFPs for higher dimensional black holes, which is the fact that this relation fixing the curvature to be, r plus 2, fixing the curvature to be negative everywhere doesn't actually fix the topology of the space-time. So previously we were studying a near horizon region that looked like a disk, but we don't necessarily need to do so. We could study, if we're just interested in this toy model, we can study space-times that include higher genuses as well. So for instance, we could study the disk in which we also include a handle. The difference will be, when evaluating the action, the difference will be that this term, which evaluates to 4 pi times the Euler characteristic of the manifold. For those of you that don't remember, the Euler characteristic is 2 minus 2 times the genus of a geometry minus the number of boundaries. So when we look at higher genus surfaces, these guys are suppressed. The action is smaller by factors of S naught. So for instance, if we compare how a disk behaves, a disk goes like e to the S naught, because this term goes like minus S naught times 1. Or the characteristic of a disk, G is 0. It's 1. It's 2 minus 1, which is 1. The factor of 4 pi simplifies. So this goes like e to the S naught, compared to a higher genus surface that goes like e to the minus S naught. And this also explains why this is a toy model, as I explained before. In our realistic model of near extremal black holes, we saw that there are powers of S naught and a whole perturbative expansion of powers of S naught that we don't have control over. So talking about these non-perturbative corrections before we understand these perturbative corrections might be a little bit mathematically ill-posed.
The kinds of corrections you mentioned at the end of last time, which are sort of subleading in e to the minus 1 over gn or whatever, the kinds of things that might involve fewer numbers of microstates that don't grow as the entropy. Kinds of things Iliesiu was raising with you.
Yes, so those...
Where would they turn up in that expansion?
Well, it depends on how many they are. I imagine that they might scale like e to the S naught to some e to the S naught times some constant.
Right.
Now, as we still see, one important feature of this expansion is what happens if at the same time as we're studying this expansion in e to the s naught, we also start scaling other parameters with e to the s naught. And in that case, for instance, what happens if we scale Lorentzian time with e to the s naught, or some Euclidean inverse temperature with e to the s naught? In those cases, what happens many times is that different topologies start to dominate, even though naively they're suppressed in e to the minus s naught if I just look at the level of the action. So the maybe different question is, if I study these subleading contributions that you're talking about, coming from different solutions in supergravity, one can also ask whether they somehow become dominant as I scale one of the parameters that I'm interested in with e to the 1 over g Newton, or e to the s naught. Okay.
We're supposed to think of this transition an infinite set of perturbative correction.
Uh-huh. Yeah, I would say so. Yes, because otherwise, yeah, I would say so. One has to include all perturbative expansion. Well, to be sure that the density of states is the sinh, and as the temperature becomes small, the density of states has a square root edge, so it goes like square root of v. One has to include all perturbative expansions in the Schwarzian, all loop an expansion to all loops. Luckily, the theory was one loop exact, so the partition function took a very nice form, which gave us this nice density of states. But in principle, it's an all loop expansion for that specific mode. And I think morally, this power of 1 over t cubed comes from resumming all loops. Okay, so this means that in our toy model, going back to our toy model, it means that we can write the gravitational partition function at the inverse temperature beta as a sum over all genera e to the s naught 2 minus 2g minus 1 dg of theta. This is the contribution from geometries that have genus G. So it has it's a 2D geometry with G holes. And in addition to that, if the gravitational path integral is supposed to sum over all geometries satisfying a certain set of boundary conditions, I can also talk about the gravitational path integral with multiple boundaries as having a similar genus expansion. Here, I mean that I have to sum over the Euler characteristic of all disconnected components of my spacetime. Let's say the disconnected components are mi, that are part of my full spacetime M. So here, for instance, at leading order, so let's say that I study, for example, a geometry with 4 boundaries. Then, leading order, I would have 4 spacetimes that would be topologically equivalent to 4 disks. These would scale as e to the 4s naught. But I could also study connected pieces. For instance, I can connect all these 4 boundaries in this toy model. So this is beta 1, beta 2, beta 3, beta 4. And this answer scales like, let's see, if we look at this formula, it has a single connected piece, so it's e to the s naught, 2 minus the 4 boundaries. It scales like e to the minus 2s naught.
What do you do to suppress all the disconnected pieces and things like that?
Sorry?
What do you do to deal with all the disconnected pieces? I can take that picture.
You sum over them.
You sum over all of them.
You sum over every possible topology that connects, that ends on these 4 boundaries.
Yeah, but okay, let's take an example.
Yeah. So
I could draw a torus in the middle of that picture.
Like this?
No, not disconnected, just in the middle. What do you do about that?
Well, first of all, torus with purely hyperbolic metric does not exist.
Okay.
Okay. But let's say put genus 2.
Exactly.
That's just the technical detail. Yeah. If we put a genus 2, then the idea is that this is roughly like a normalization factor. So we can sum over all of them, but the meaning of this partition function as a function of beta 1 through beta n is that it just captures the contribution of space-times that are connected to boundaries. So we can sum over all of them and then divide the path integral by an integral over all geometries that have no asymptotic boundary. And essentially everything that doesn't have an asymptotic boundary will drop out. So it's just about the normalization of the partition function. Great. By the way, this is not the leading answer that is subleading. So this is the leading answer. It goes like e to the 4s naught. Disks are always leading, and then e to the s naught expansion. What is the leading? What is the next geometry that contributes at subleading order? Ooh. Yes, it involves a cylinder. So for instance, I can replace this by a cylinder. And if I compute the Euler characteristic, this contributes a factor of e to the s naught. This contributes a factor of e to the s naught. And cylinders have Euler characteristic 0. So this goes like e to the 2s naught. However, there is another contribution at the same order, which is if I put 3 disks and the genus 1 surface, this also contributes a factor of e to the 2s naught. So you see, the point is that there's many, many types of surfaces that I can sum over, and I have to be careful to really understand the contribution of each of them. So in order to study the partition function of an arbitrary genus G surface, I have to explain what the building blocks are.
So here we don't consider non-orientable space.
Sorry?
We don't consider non-orientable contributions here.
We can consider non-orientable configurations. I can define a toy model in which I either sum over surfaces with fixed orientation or also sum over non-orientable surfaces. They both have a different meaning. Maybe next lecture, I'll mention a little bit what the meaning of the non-orientable surfaces is. So for now, let's assume that we're summing over spacetimes that are orientable. So no Klein bottles and fancy things like that. So my building block will rely on the following property of hyperbolic geometry, namely that there exists closed geodesics that are unique. So there's a single one in any homotopy class of a geometry. Homotopy class. And the idea will be to use these geodesics to cut the space-time into a bunch of components that I can, whose contribution I can explicitly compute, and then glue space-time back together to obtain what a partitional, what ZG is.
Sorry, and this is the new model of non-perturbative corrections explicitly for the calculation of the partition function, right?
Yes, but
correlation functions.
I can also compute correlation functions in this model because at the end of the day, in ADS2, the propagator only depended on distances between points. So I can, for instance, compute correlation functions by summing over all geodesics between two boundary points to compute the propagator between those two boundary points. What this model would not take into account, however, is that in principle, in a correlation function, that field is coupled to gravity, right? So it doesn't take into account the one-loop determinant of that field as it back reacts on the space-time. Okay, so let's draw, let's say, a genus 2 surface. And as I said, there's a unique geodesic in each homotopy class. And let's draw a couple of them. So there's one, a unique one that's homotopic to the asymptotic boundary, which is not a geodesic. And, you know, there's others here. So for instance, maybe I'll draw here and here instead. So for instance, you can think that you can decompose this geometry into a sum of a geometry that only has one asymptotic boundary and one closed geodesic boundary, plus a geometry that, sorry, I keep getting this wrong. I want to draw one that looks like a pair of hands. Plus genus 1 surfaces, and so on and so forth. So the idea is to cut the space-time into as many pieces as possible and to determine what the contribution of these basic shapes are. Now, there's one thing that's very important throughout this entire calculation, and this is like going to make the calculation extremely difficult. Namely, when I do a gravitational path integral, I have to integrate over all possible metrics, but I have to be careful to quotient by by all metrics related by diffeomorphisms. Now, we were careful actually in the previous computation in JP about the role of small and large diffeomorphisms. Namely, small diffeomorphisms we were able to quotient out by just essentially fixing the metric to take a certain form, and we only worked with the metric in that form. And the large diffeomorphisms that acted on the boundary, actually were very important in the previous lecture because they were essentially identified with the JP we were talking about. But there's another notion of large diffeomorphisms that appears even for manifolds without an asymptotic boundary, which is the set of all diffeomorphisms that are not smoothly connected to the identity. Now, on a higher genus geometry, this set of transformations forms a non-abelian group called the mapping class group of a space-time or of a manifold. The idea is that if I want to throw, in addition to throwing out all small diffeomorphisms, I want to throw out quotient my path integral by the mapping class group. So I don't want to overcount geometries that are related by a large diffeomorphism. And we'll see what that very concretely means in a few minutes. So,
concerned about Lorentzian continuation. Why are you looking at the building blocks? I mean, this is going to give you a bunch of saddle regime, which presumably you count because they're saddle points. Why is the Lorentzian sectioning so important to you?
oh, this is not a Lorentzian sectioning.
You're cutting it to pieces which have Lorentzian sections. Isn't that the point?
No. The point is just, first of all, none of these Euclidean geometries actually turn out to be saddle points for a reason that I'll mention later. Essentially, while I'm satisfying the equation of motion r plus 2 equals 0, it turns out that the dilaton equation of motion cannot be satisfied on this space-time. But the sectioning has a different role. It has the role of trying to understand what these, partition functions are by reducing it to elements that have smaller genus that I might be able to compute. And this is very analogous to, for instance, if any of you have studied how 2D gauge theories are quantized, like 2D Yang-Mills or 2D Maxwell theory. To obtain the partition function of a surface of genus G, one decomposes the manifold into a sum of what are called pairs of pans. A pair of pans is just like a freehold sphere, and it's this shape. So it has genus 0 and free boundaries. And every surface can be every higher genus surface can be decomposed into a sum of pair of pans. For instance, here, if I also cut the manifold here and here and open it up, I obtain 3 pairs of pans. Now, the subtlety is, again, that this decomposition into pairs of pans and the gluing back to obtain the entire geometry is not, does not treat these large diffeomorphisms correctly. So as opposed to 2D gauge theories, where it's pretty easy to put together these building blocks and obtain the partition function as genus G, here, when doing the cuts, we have to just be very careful to account for the mapping class group. And this is actually what a mathematician by the name of Miriam Mirzakhani did. So she computed the volumes of all these higher genus surfaces, accounting for the mapping class group. And I'll actually describe what she did more explicitly. So let's start with one of the shapes that's present whenever we have an asymptotic boundary, namely this shape that has one asymptotic boundary and one geodesic. So here I essentially want to compute the path integral, including all boundary wiggles, but somehow impose that I have a geodesic inside my space-time, Euclidean space-time. It's not a Lorentzian sectioning or anything like that, that has a proper length p. So I want to ask, how is this hole that I inserted in the space-time encoded in the boundary wiggles? Since we saw that the only contribution to the partition function on the disk came from boundary wiggles. Here, it's that should also be true. The only given Hagen-York term is here, right? My action still just evaluates to an integral over phi b times k minus 1 evaluated on this geometry. So first, how is it actually possible to draw a closed geodesic on a hyperbolic surface? For instance, if I look at the upper half plane, all geodesics go outside of the upper half plane. So how is it then possible to draw a closed geodesic? Well, we have a good analog in flat space, right? While I can't draw a closed geodesic on a piece of paper, it's just a line. If I compactify that piece of paper into a cylinder, then there's a closed geodesic around the cylinder. So essentially, the difference in that case is that I have to consider, just like in flat space, I have to consider a quotient of my plane in order to construct the cylinder. Here, I have to consider a quotient of the upper half plane in order to consider a space-time that has a closed geodesic. So to consider a quotient of the upper half plane, what we can essentially do is identify these two geodesics that are related by a specific SL2R transformation. So if these two geodesics are identified, then I can draw a geodesic that's another geodesic that's, let's say, perpendicular to both of them. And then when I do the quotient of the space-time, I obtain a hyperbolic surface that has this closed geodesic on it, whose length is b. And the asymptotic boundary, I'll draw ahead, begins and ends on these two geodesics and goes all the way out to infinity. So the difference between the disk case and this higher genus case on which I have, or multi-boundary case on which I have a closed geodesic, is that the boundary conditions that I have to consider for my Schwarzian field, or my Schwarzian reparameterization mode, T of tau, previously on the disk, I had to impose that this red circle closes onto itself. So I had to impose that T of tau is equal to T of tau plus beta on a trumpet. I have to impose that T of tau comes back to itself up to an SL2R transformation. This is exactly what you would think of if you studied the analogous boundary conditions when you take a z quotient of the plane. So let's see more specifically what boundary conditions. So it's convenient to parameterize the metric on this geometry in the following way. So this is still a geometry that has r equal -2. But the geometry of the Poincare disk, the metric of the Poincare disk, usually has sinh squared here instead of cosh. The difference, if we put cosh while r remains equal to -2, notice that now when sigma is equal to 0, then the sigma equal to 0 locus is actually a geodesic for any theta. So if I identify theta with theta plus b, then that's precisely the geodesic of length b that I draw above. What did I do before? Well, before I imposed that the induced metric on the asymptotic boundary is fixed to be some 1 over epsilon squared. So I can do the same thing here. So one can impose that sigma prime is a function of tau squared plus cosh squared sigma of tau times theta prime squared is like 1 over epsilon squared. And from this, you can solve again for theta as a function of sigma. Sorry, for sigma as a function of theta tau. And plug everything into the formula for the extrinsic curvature. And you'll find that the extrinsic curvature on the surface as a function of theta of tau is 1 plus epsilon squared Schwarzian of e to the minus theta of tau. So this was the variable t of tau that we encountered in our second lecture. Now, the difference is that here, notice that theta goes back to itself after a shift by b, which means that in order for the asymptotic boundary to start at this point and end at this point, I have to impose that theta of tau is equal to theta of tau plus beta plus b, which implies that t of tau is t of tau plus beta e to the minus b. And this, we can write this as an SL2R transformation. It's simply the SL2R transformation by doing the following stupid thing. It's t of tau plus b e to the minus beta over 2 divided by e to the b over 2. So I can write this as identifying t coming back to itself as an SL2R transformation, where the SL2R transformation is just e to the minus b over 2, 0, 0, e to the b over 2. Okay. So essentially, I still encounter to compute the gravitational path integral on this surface. I still encounter the Schwarzian, but with these funny boundary conditions. So what's the role of these boundary conditions? Well, the equations of motion remain the same. Those are independent of the boundary conditions. But the solutions are now different. Namely, even though the Schwarzian is a constant due to the equations of motion, theta of tau is now d tau over beta, which means that the Schwarzian of e to the minus theta tau actually now depends on the parameter little b. So it's minus beta squared over 2 beta, and this should be compared with the previous answer, which I think was 2 pi squared over beta times m break. Let me put a break here as well, just to keep track of where the coupling appears. Sorry, no, and the Schwarzian itself, it doesn't appear. So this was this. This is trumpet. And remember, previously I emphasized that the fact that the Schwarzian on shell is positive means that the extrinsic curvature is bigger than 1 using this formula, which means that the solution is a circle of constant curvature that's embedded in the upper half plane. Now we find that k is slightly smaller than 1, which means that I'm looking on shell, I'm looking at a solution that's a circle that goes slightly outside of the upper half plane. But because I'm considering a z quotient of the upper half plane, the red circle doesn't have to be fully contained in the upper half plane in order for this to be a closed solution. Great. So now I can consider quantum fluctuations. Just as before, what did I do? I took tau of u and expanded it around the saddle using some modes epsilon of u, plugged in these modes into the Schwarz inaction that appeared in the extrinsic curvature, and evaluated things at one loop order. So let me write what the quadratic expansion of the action is. So I obtain an integral over d epsilon n, d epsilon minus n, e to the minus 4 pi squared epsilon n, epsilon minus n, over beta times m break, times n squared, times n squared plus b squared over 2 beta squared. So this should be compared to the -1 that I encountered on the disk, if you remember from a few days ago. So on the disk, this b squared over 2 pi squared was just replaced by -1. Now you see that this having the -1 versus the b squared over 2 beta squared causes a very big difference. Namely, I didn't tell you what modes we should integrate over here. So when on the disk, if I have n squared minus 1, it means that the modes with n equals 0, 1, and -1, those were the SL2R transformations, have 0 weight. But now there are 2 modes, namely the n equal 1 and -1 modes, that now gain the non-zero weight. And this is just a sign of the fact that on this geometry, the SL2R transformation is broken down to a subgroup due to the presence of this closed geodesic. Namely, the isometry of this manifold is somewhat clear. I can rotate it by along this direction, but if I do translations, then what happens is that I move the location of the geodesic, closed geodesic, relative to the boundary. And that's what changes the weight that I see in the extrinsic curvature. So essentially, here I have to consider the contribution of all modes except the n equal to 0 mode. And the difference that occurs due to this different isometry is that the partition function contains a different power of beta. While previously on the disk, I saw that the power was given by beta to the free half. Now, because I have a smaller isometry group and the power of beta we saw just counted the number of 0 modes in this quadratic expansion of the action, one finds that the trumpet partition function is given by 1 over 2 pi over beta and break to the 1/2 e to the minus beta b squared over 2 beta and break. So this was just the saddle, and this is the one loop fluctuation. which has a different power of beta precisely because of the difference in the isometry. There's a small subtlety in here, which is that I didn't actually write the path integral measure in this model. The path integral measure comes from essentially a symplectic form that I can write in the gauge theory formulation of this model. And the path integral measure turns out to be such that all factors of little b cancel out in the one-loop determinant. So essentially, that's why this contribution in the one-loop determinant is completely independent of the parameter little b. Okay.
And I still have one loop exactness.
And you still have one-loop exactness, yeah, because it's the same. It's the same theory. It's the same theory, yeah. The integration space is still a symplectic manifold, namely diff S1 over U1, which is my integration space, is still symplectic geometry, and one can apply the same localization argument that people had argued for the disk. So now we have one basic ingredient. So let's try to construct the partition function of a geometry that can be constructed out of these basic ingredients. Namely, let's try to construct the partition function of a cylinder that connects two asymptotic boundaries. One of proper length beta 1, and the other with proper renormalized length beta 2. And I told you that every hyperbolic surface has a unique geodesic in each homotopy class. Here, there's a single, all curves that wrap the cycle are homotopic to each other. So I can cut, and which don't wind, I mean. So I can cut my geometry along this geodesic and separate it into two trumpets. So the only thing I have to discuss in order to glue these two trumpets is what the gluing measure along these geodesic is. And there are two parameters in each gluing. Namely, one is the size of the closed geodesic, B, and the other one is the relative twist between the left side, the left trumpet, and the right trumpet. So this is size, and this is relative twist. And the integration measure just comes from a form that's called the Weil-Petersson form. Which, for this specific geometry, means that we can just glue these two trumpets with a factor of dB times d tau. So a flat measure in size and twist. But the question is, what is the integration range? Bless you. So for that, to discuss the integration range, I want to discuss a little bit more the meaning of this term. So let's rewrite the metric that I wrote previously as ds squared equals d rho squared plus cosh squared rho. And instead of writing that theta variable that I wrote earlier, I can write the form b times dx plus tau delta of rho d rho squared. So this was just d theta squared, which means that theta, so here x is identified with x plus 1, in order for the closed geodesic is located at rho equals 0 to have proper length p. But this means writing the metric in this form means that I performed the diffeomorphism in which I took theta to be equal to b times x plus tau times a theta function. Sorry, this is a theta function. Let me just write it like this. Rho. So this is 1 for positive rho and 0 for negative rho. It should be different than the theta coordinate. But the important thing that I wanted to see here is that in this metric, the boundaries, one is located at rho going to minus infinity, one is located at rho going to plus infinity. And this parameter, this step function that activates for positive rho means that when writing the metric in this form, I'm performing large diffeomorphism for the space-time when rho goes to plus infinity, because this part of the coordinate transformation doesn't vanish as rho goes to infinity. So it affects the relative position of the right boundary with respect to that of the left boundary. So this I can think of as a large diffeom. Except one has to keep in mind that theta is identified with theta plus b. So on the right boundary, or at any point in the geometry, there's no meaning the values of tau that are shifted by b can be identified with each other, which means that I'm forced to identify geometries that have a twist that is shifted by b with geometry whose twist is just tau. So that means that the integration range for the tau variable should just be from 0 to b. It gives you a factor of b.
Sorry, it's not a problem that you break the smoothness of the coordinate. Introducing.
No, here it wasn't actually that important that. Yeah, it's not actually that important that I take a theta function here. It can be replaced by any function that's smooth on some interval.
Okay.
In such a way that it's 0 at the beginning of the interval and 1 at the end of the interval. So you can still, or you can choose some function that vanishes on this boundary and is 1 on the right boundary. And you will still get the same twist by tau.
Okay.
Here, it's easier. The reason why I put this delta function is because it makes it obvious that you can just localize the twist on this geodesic junction in between the two trumpets. But yeah, but one can do this more generally. Perhaps I should say this, say it at this point, that this emphasizes that the mapping class group of this geometry, which is a cylinder, is just Z. Because geometries that have twists related by tau related by tau plus b should be identified with each other. They're diffeomorphic to each other, right? Okay. So using the fact that integral of d tau is just phi, I can now write down the partition function of a cylinder. Oh, sorry. First with B1, B2. As just, so first there's a factor that goes like the Euler characteristic, which is e to the 0 times s naught, times the integral from 0 to infinity. This, the range over b is unbounded. The geodesic can be as big as I want. A b db, z trumpet, of beta 1, the trumpet of beta 2. Now, notice that the b dependence, little b dependence of z trumpet is very simple. It's just a Gaussian. So I can do this integral explicitly. And what you get is 1 over 2 pi square root of b1, b2 divided by b1 plus beta 1 plus beta 2. Okay. Now, out of curiosity, since the spectral form factor computes contribution of a path integral that has two boundaries, one which is beta plus it, and one which is beta minus it. Let's see how this cylinder contribution goes if we think about it as a contribution to the spectral form factor. So plugging in beta 1 and beta 2 to have the following form, I find that Z02 goes like 1 over 2 pi. The top thing just evaluates the square root of beta squared plus t squared. And the bottom thing just evaluates to 2 beta, right? Simple algebra. So in the limit of large T, T much larger than beta, this cylinder contribution goes like 1 over 2 pi T over 2 beta. And if I view this as one contribution to the spectral form factor that comes in addition to the disk level contribution, I saw previously at the beginning of this lecture that the disk contribution went like e to the 2s naught divided by m breaking times t cubed. And now this contribution goes like 1 over 2 pi, goes to like some number, times t over 2 beta, which means that while this is decaying, this one is growing. So if I draw the spectral form factor once again, it went like a power law, like p cubed, so it's a line on the log-log plot, but these two curves intersect, and eventually the cylinder contribution starts dominating over the product of two disks. And this happens at a time, so if I find when the order of magnitude of these two contributions becomes the same, it's at a time that's proportional to e to the s naught over 2. So at least the leading order corrections to the spectral form factor seem to give a growing piece in T over beta, which is exactly the type of contribution that we were looking for in order for our black holes to be equivalent to conventional quantum systems.
What's the scale of the as well? Is it m right or is it p inverse? Is it p?
It's both, right? So we have to solve e to the 2s naught divided by m break cubed is equal to t to the 4th and a factor of 2 beta here. So I take the 4th order root. Let's drop this factor of 2. Order more factors in front. So the thing that multiplies e to the s naught over 2 is beta to the 1 quarter and break to the 3 quarters. But the important factor is the c to the s naught over 2. Sorry, not 4. And that means that at exponentially late times, I can have things that naively seem non-perturbatively suppressed kick in, and become dominant at late times. So now the question is how this plot continues. And in order to find the shape of this plot, one has to know more complicated building blocks for even more complicated topologies. So the next step that we will study in tomorrow's lecture is how to compute the contribution that involves surfaces that have arbitrary genus and arbitrary number of boundaries. Okay, thank you very much. That was it for today. Question?
Does the M break come into anything in when you have the wormhole contribution?
Yeah, so let's see. I think in there, M break completely simplifies. Namely, the integral over BdB, e to the minus b squared over 2 beta M break. The b factors, sorry, the M break factors completely simplify with the ones from the one loop determinant, if I remember correctly. Yeah, it does, right? Because I have a factor of BdB. Yeah, and that's because you see things only depend on beta over M break. So here, essentially, if I would have rewritten things in terms of beta 1 over M break and beta 2 over M break, the coupling would have completely vanished in this final answer. So yeah, perhaps one nice thing about the cylinder contribution is that it's completely independent of the coupling of the boundary theory, which is another funny feature.
That won't happen for higher order.
It will not happen for higher order terms. No, this comes from the fact that this cylinder piece is universal, and as we still see, it's connected to a universal piece that also appears in the spectral form factor of matrix integrals. By the way, just a show of hands, I saw that Anard gave a set of lectures in September, October. Did most people attend that set of lectures? Because the next lecture is actually connected to his set of lectures. So, okay, okay.
It's online. It's online.
Okay, requirement for next lecture for tomorrow. Watch all of the 5 lectures.
Yeah, 10 hours.
No, I'm kidding. I'm kidding.
You're right. Will give us a crash course in a couple hours.
Right.
Okay.
So, no questions from online?
Questions?
Yeah.
Okay, so see you tomorrow. Thank you.